you so much, everyone, for participating. I can see we are reaching 150 participants now. So, and the number is still growing. So I think having these virtual meetings is really a wonderful thing. So thanks a lot, Gitte, representing the SIAM conference organizers team for setting this up. Really, thanks a lot. Just some practical things. I believe we've decided that questions should please be asked via the chat. And we will get back to these questions at the end of the talk. Yeah, and then I guess it's on me to introduce the speaker. So Weinan is a professor of mathematics at Princeton University and Chang Yang visiting professor at Peking University. Weinan did his master's at the Chinese Academy of Sciences and his PhD at UCLA. His research has been acknowledged by several awards and honors, and I will not report all of them because there are many, but just a few. So Weinan received the Collards Prize of ICIAM in 2003. He is fellow elect of SIAM, which he became in 2009. He received the SIAM Ralph E. Kleinman Prize in 2009, and he is member elect of the Chinese Academy of Sciences. Weinan made several seminal contributions to various areas of applied mathematics, applied PDEs, multiscale, and stochastic problems. And I would say for the last couple of years, made several substantial contributions to the mathematical theory of machine learning and its role in the mathematical modeling and simulation. So some of the insights that he gained through the work that he did on this topic, he will share with us this afternoon or this morning in this session today. I really look forward to this, Weinan, and I'll hand over the stage to you.
Thank you, Carla, for the introduction. What I wanted to do today is to give a sort of a perspective machine learning from the viewpoint of a numerical analysis. But there's a very difference between classical numerical analysis, namely approximation theory, optimization, finite elements, numerical methods for PDEs, ODEs, and stuff like that. In that problems in machine learning are almost always very high dimensional. So that's the new twist. This work, most of the work is joint work with two former students of mine, Chao Ma and Lei Wu. And actually the slides are available on my web. The papers and slides are available on my webpage. Okay, so this is an outline, and it's a 1 hour talk. So I'm sure at the end of the talk, I'm going to rush through, maybe I'll even skip one of the sections. So the basic example, supervised learning, is the following. We're given a data set S, where these Y's are labels, are called labels. So they're given by a function f star evaluated at the points xj. F star is called the target function. So our task is to learn or approximate f star as accurately as possible from this data set. So right away we know this problem is a problem about function approximation. If f star is discrete valued, we call this a classification problem. If f star is continuous valued, we call this regression problem. And throughout this talk, we're going to assume the domain of interest is a unit cube. And then these data points xj is sampled from a fixed distribution mu, which is unknown. In practice, we divide the data set into two parts. One subset called training set, and another subset called testing set. So the training set is used to produce our model, and the testing set is used to test our model. Here is a typical example. So this is the well-known CFAR data set. We're given these images, and we want to classify these images into 10 categories: frogs, dogs, horse, and stuff like that. So each image can be viewed, is a 32 by 32 pixel image. So it can be viewed as a point in 32 by 32 by 3 dimensional space. So 3000 dimensional space, where 3 comes from the dimension of the color. So this problem, abstractly speaking, can be viewed as approximating a function in 3072 dimensional space into 10 values, discrete a set of 10 values. Now, this is another example. This example is a regression example. This example comes from molecular dynamics, where we try to track the dynamics of atoms. So if you have a system of n atoms, and you would want to just solve Newton's equation to study the dynamics of these n atoms, then of course you need this function which describes the interaction between these atoms. This is the potential energy surface. It's called potential energy surface in molecular dynamics. That's a function of all these variables, many variables if you have many atoms. Now, here I'm showing you the result of a deep learning kind of model for this function that we produced. And the horizontal axis is the result of quantum mechanics model. So here, density functional theory. It's a version of quantum mechanics model. The vertical axis is the prediction of the machine learning model. You can see that the scatter away from the diagonal, which represents the error in the model, is quite comparable to the error in the DFT model itself across a very wide spectrums of materials or molecules. So ranging from small molecules, this is aspirin, ethanol, to very highly complicated materials like high entropy alloy. So this is an alloy with 5 components. So these are the kind of system that's very difficult to model empirically. And big molecules like here, oxidides, across a very wide spectrum of systems, the accuracy is comparable to that of the quantum mechanics. So these are the kind of applications that I'm personally interested in. They're not the standard applications of machine learning to classical artificial intelligence, but these are the applications to what we used to work on, computational science and scientific computing. So this is a list of, I would say, where the frontier is as far as machine learning application to computational science and scientific computing is concerned. They're all concerned with very high dimensional problems. They're all problems that 5 years ago we would not have imagined to be able to deal with, ranging from PDEs in hundreds, thousands of dimensions, control problems in hundreds, thousands of dimensions, to molecular dynamics, one example I just showed, to quantum many-body problem solving Schrödinger equations in very high dimensions, to multi-scale modeling in cases for which there are no separation of scales. Let me just give you a kind of one typical result showing the impact that these kind of techniques have had. So here, the aim, the objective, is to molecular dynamics, but with quantum accuracy. So this is called ab initio molecular dynamics. In the old days, meaning 2 years ago, we were able to do like thousands of atoms. So this is parallel molecular dynamics, very celebrated piece of work in chemistry and material science. So 2 years ago, we can handle 1,000 atoms, and that's already considered to be large system. But now we can handle 100 million atoms. So this is the order of magnitude, 5 orders of magnitude, and with quantum accuracy. So this is remarkable because with this kind of capability, we can now looking at realistic systems, something we were not able to do. And we would actually, as a matter of fact, 2 or 3 years ago, we would not even have imagined that we can do. Okay, but this is not what I want to emphasize. I want to emphasize the mathematical foundation of machine learning. So I would like to address this problem from 3 viewpoints. The first is looking at the error. So how big are the error? From this, we want to come to the conclusion that there are good solutions do exist. The second is how do we find these good solutions? So the training algorithms that people use in machine learning. So everybody in machine learning knows that it's possible many times to produce good results, but the process of doing that is very subtle. You have to tune parameters. You have to be very experienced. So why is this the case? We want to look at why things can be successful and what are the subtleties are. Unfortunately, I wouldn't be able to discuss all the subtleties because we don't know of them. And even for the ones we do understand, I don't have time to explain all of them. So I'll just give one example here. And thirdly, in mathematics, we emphasize problems that are well posed as opposed to ill-posed problems. So I want to ask the question, how do we pose machine learning problems so that we are pretty sure it's well posed in some sense, meaning that things are robust, not so subtle as the current machine learning algorithms are. So these are the three things I want to talk about. Obviously, not everything is understood, but I want to explain to you the basic ideas. So let's go back to the origin. This is the standard procedure for supervised learning. It has 3 steps. The first step is to choose a hypothesis space, which is just a set of trial functions. We're going to use the set of trial functions to approximate our target function f star. Target function f star. The second step is to formulate a variational problem, namely the loss function. The third step is to solve that variational problem. So because we only know the function at a finite set of data, so we have to work with this what is called empirical risk. So we try to fit the function to the data we already know. So this is called the empirical risk. But in reality, what we're really interested in is not just to fit the data we know, but also to fit the data we don't know. So in reality, what we're really interested in is to minimize what is called the population risk. So also called generalization error. But the most practical common terminology will be that this is called the test error. This is called the training error. So we want to construct all 3 steps so that this population risk or test accuracy is the best. The important parameters are n, which is the dimensionality of the hypothesis space. In the hypothesis space, you can choose polynomials, wavelets, and neural network models. So n is an important parameter. That's the number of degrees of freedom. N is the number of data that we want to fit. T is the number of steps we're going to take in whatever optimization algorithm we're going to work with. And D is the dimensionality. So we're going to be interested in the case for which these 3 parameters go to infinity, but D is very, very large. So thinking about problems in high dimension, here is perhaps the best benchmark, namely high dimensional integration. So we want to integrate this function in millions of dimensions. And right now, this is a very routine thing to do in statistical physics. So if you use Simpson's rule or trapezoidal rule, you would have this kind of an error where you have this D here. So everything else is not so important. What's important is this D. The fact that you have the D here is a signal of what is called cursive dimensionality. This is perhaps the most important terminology for this talk. If you want to reduce this factor by a factor of 10, this n should be n. Sorry. If you want to reduce by a factor of 10, then you need the number of degrees of freedom to increase by 10 to the d. So if this d is a million, this obviously is a number that's impossible. So grid-based rules are not so good. But then if you use Monte Carlo integration, namely we randomly sample the uniform distribution, then we have this exact formula, namely the error in expectation squared is variance over n. There's no dimensionality dependence here. That's the most important thing. And the variance, the constant is given by this variance. So this red rate is dimension dependent, but of course, this constant can still be huge. So therefore, we have to think about all kinds of techniques to do variance reduction. So this is the golden standards we're going to apply in the context of approximation theory for supervised learning, in the context of solving PDEs for reinforcement learning, etc. So keep this as a background. So going back to the error, so f star is a target function, f hat is the output of the machine learning model, whatever machine learning model we're working on. So this error can be decomposed into 2 terms. Here, the fm is the best approximation of f star in the hypothesis space. So the first term is called approximation error. So this approximation error only depends the choice of the hypothesis space, nothing else. The second term is whatever is left, the fact that you only have finite piece of data that produces additional error. So we call this estimation error. So let's look at each. So first look at the approximation error. Traditionally, when we do approximation functions, we use polynomials, piecewise polynomials, splines, wavelets, all kind of stuff like that. We would have this kind of error estimate. You remember M is degrees of freedom. So notice that there's this D here, the appearance of D in the exponent. So this is the signal that there's a curse of dimensionality. And that, so meaning that these ideas are not good in high dimensions. Turning into estimation error. So that's the difference between training and testing. So here is a classical example illustrating the estimation error. So this is a problem of interpolating a very nice function, 1 over 1 plus 25x squared. Sorry, there's a 25 missing. 25x squared on uniform grids with high order polynomials. So you can see on the grid points, these are the training data. We have exact, the prediction is exact, but away from the grid points, we have big error. So this is called a wrong phenomenon. And here is in an illustration that the discrepancy between the training error and testing error can be very large. So these kind of machine learning models are not very good. So why is this so? Let's look at this difference between training and testing errors, which, this is the training, this is the testing error. This is the training error, empirical risk. This is the testing error, population risk. The difference between the two is what is shown here. The difference between, that's also called generalization gap. Now, superficially, on the first side, you might think, well, this is nothing but the Monte Carlo discretization of this. So maybe it's 1 over square root of n, and we discussed earlier. This is not the case, because what we're interested in is the result of this difference for the machine learning model that's produced. But the machine learning model, namely f hat, is highly correlated with the data. So the argument I used before doesn't work here. In general, as a matter of fact, we should not expect this 1 over square root of n error to hold. As a matter of fact, if you choose your hypothesis space to be the unit ball of Lipschitz functions, then this generalization gap can be as large as this. And you can see that there's also an occurrence of D here, showing that there is cursive dimensionality. So the choice of hypothesis space enters here in a different way. Before, when we look at the approximation error, we want this hypothesis space to be big, because if the hypothesis space is big, then this error will be small. So now we want the hypothesis space to be small, because if you have a hypothesis space is big that has too many degrees of freedom, you would see things like this. You will have seen models that fits the data, but away from the data, things are out of control. So here we want the hypothesis space to be small. So this balance between training error and testing error, between approximation error and estimation error is sort of the key. Now, how do we control this generalization gap? And in machine learning, this is controlled by a notion called Riemann complexity. So this is something that I wouldn't be able to explain during this talk. If you already know, you already know. If you don't know, then maybe take some time to think about it. So one can define, one can define a notion, a quantity, which is associated with any hypothesis space, given the data. Given a set of data, we can associate a notion of complexity for any hypothesis space. And that complexity controls the generalization gap that we're interested in. Okay, this generalization gap we're interested in. Up to small terms. So these are small terms that occurs in machine learning all the time. As you can see, this theorem states that with high probability, so give any data with probability 1 minus, give any delta with probability 1 minus delta, over the sample, over the training set, that the generalization gap is small, is controlled by Raman complexity up to these terms that are not so important. So these are sort of the typical kind of statements that occurs in machine learning. So here, technically speaking, concentration inequality plays a role in these kinds of statements. So summarize, we can just divide all machine learning models in two kinds. The kind that do suffer from cursive dimensionality, whether it's in the approximation error because the hypothesis space is too small, or in the estimation error, where when the hypothesis space is too large. Okay, so traditional approximation theory, all the models in traditional approximation theory, traditional numerical analysis, falls into this category. The other category are models that do not suffer from cursive dimensionality, then in which case the golden standards, if you remember, for this generalization error is that it's 1 over square root of m and 1 over square root of n. So these are error rates that are comparable to Monte Carlo. So these are our golden standards. So we're going to show that these models, random feature models, two-layer neural network models, deep residual neural network models, all fall into this second category. As a matter of fact, you might even ask, what about these constants? Because these constants here play the role of variance in Monte Carlo method. And remember, variance reduction is an important concept in Monte Carlo method. I'm going to argue that going through from here to here to here is actually a variance reduction process. The constant here in this model is the smallest among all three models. Okay, so this is the topic of next section. But next section, I will only talk about, so in the next three sections, I'll discuss the three components that I mentioned earlier here. Boy, where did it go? Yeah, here. For two relatively simple models. One is a linear model, namely the random feature model. That's a linear model. Another is a simplest neural network model, namely two-layer neural network model. And in the last section, section 5 here, I'm going to use these three, the sort of the viewpoints that we used in these three sections to analyze the deep neural network model, namely the residual neural network model. But as I think by that time, my time will run out. Good. So I might have to skip that. So first let's look at random feature model. So let phi be a collection of features depending on a random variable W. So W is a random variable here. For example, we can choose phi to be function like this, where sigma is nonlinear, some nonlinear function, sigmoid, for example, Gaussian or ReLU, some nonlinear function. Pi is the probability distribution for the random variable W. So let's take a IID sample of pi, call that omega Wj, and then formulate a hypothesis space that's a linear combination of these features, random features from this set, from this fixed sample. So this is the hypothesis space for the random feature model. We can just fit the target function using these kinds of functions. So the degrees of freedom here are the AJs, these coefficients AJs. So this is the linear function space. We will need the following norm. Now this norm is might be a little bit strange, but let me just say that if P is equal to 2, then this norm is the same as the norm in the reproducing kernel Hilbert space with the following kernel. This kernel is defined by the random features. We just take this expectation, and that defines a kernel. With that kernel, there is a reproducing kernel Hilbert space. Then if P is equal to 2, then this is the same space. This is an LP generalization of that reproducing kernel Hilbert space. So why do we need this space? Why do we need this space? if you recall your classical approximation theory, we need Bessel spaces, subtle spaces, you know, stuff like that. So here, these kind of spaces plays the role of Bessel space and subtle space in classical approximation theory. Why do I say that? Because with these spaces, with these norms, we can prove direct and inverse approximation theorem, which basically says that this space is the most natural space associated with this random feature model, in the sense that if a function is in the space, then we can have a good approximation property for that function. So good in the sense that Monte Carlo type of convergence rates holds with coefficient, with error constant given by the norm of that space. Conversely, if you have a function that can be approximated by random feature models with coefficients being bounded, then that function has to be in the right space. So this is the kind of a classical result in approximation theory that we want, except here now, our convergence rate is almost fixed because the best we can do is Monte Carlo, and we have to deal with different kinds of spaces. So with that in the background, we can consider this regularized model. So with the standard scaling, where lambda is a constant, some fixed constant, and this is sort of the norm, the generalization of these kinds of norms for the hypothesis space. So hypothesis space is discrete. This is the continuous. So the generalization of these norms to here, extension of these norms to here. So that goes in the regularization. So if you think about this, more or less a standard regularized model, so this is the empirical risk. So just fit the training data. This is the training error. Any global minimizer of this regularized model satisfies this, this kind of estimate we wanted. So with 1 over n, 1 over square root of n, and error constants are just given by the norms. Okay, so so these are kinds of a priori estimates that we're interested in. We call this a priori estimates because the right-hand side depends only on the target function. It doesn't depend on the solution. In machine learning, this is very rare. In machine learning, typically people have what we would call a posteriori error estimates, because the right-hand side depends on the solution that you produce from your model. So here, these are a priori estimates. So that's for random feature model. It's a linear model. So now let's look at a two-layer neural network model. This looks almost the same, exactly the same as the hypothesis space here, except here the WJs are given. Here the WJs in the neural networks, WJs are also part of the parameters you want to optimize with. So in this context, we also need to define the right space. And this space, the right space here is what we call the barren space. So what is the barren space? First of all, we only want to consider functions that has this kind of representation. So where does this come from? Well, this is nothing but the continuum analog of this expression, where we use rho to denote the probability distribution of the AJs and WJs. So this is a continuous analog of these. Natural question is, what kind of functions admits this kind of representation? So that's another story I don't want to get into. There are some results in that direction, but I don't want to get into that. But if a function has this representation, then we can define the following norm. Infimum is taken over all possible rho for which this representation holds. So this is the analog of the representing kernel Hilbert space that defined earlier. So we call this barren space to honor the work that Barron has done since early 90s. So he's worked on this a long time. So now if we have, so barren space is going to be the right space. We're going to argue barren space is going to be the right space for the two-layer neural network model. Next slide explains that barren space is actually bigger, much bigger than reproducing kernel Hilbert space, and norms are smaller. But since time is sort of short, I will skip this. just want to say that with barren space, then one can prove the same kinds of direct and inverse approximation theorems for neural networks, where the norms are replaced by the barren space norms. And similarly, if you consider regularized models, where this is the analog of a barren norm in a discrete setting, if you consider this sort of a more or less standard regularized model, one can show that all minimizers of this regularized model satisfies the kind of approximation results we wanted. Again, the population risk or test accuracy, the test error is less than 1/m, 1/squared of n, with these norms now replaced by barren norms. So this is the sort of the error analysis. Now, want to look at the optimization problem. As I said, the understanding of the optimization algorithm in machine learning is very far from complete. So over here, I'm just giving you one illustration of the kind of subtlety that might arise. So to do that, I'll look at the random feature model, which is a simple linear model. So if you use the simplest optimization algorithm, namely gradient descent, that's this. The coefficient follows the gradient descent of the empirical risk. Then you would get this linear system of ODEs with a kernel or with a gram matrix given by the following this expression. So this is a very simple linear problem. Now, we're just going to look at one case when m and n are kind of close. These two parameters are kind of close. If you, so in that case, if you look at the test error for a simple data set, MNIST, this is the handwritten digits data set, the simplest real data set. The error looks like this. It goes down and then almost blows up and then goes down again. And the blow up, almost blow up occurs precisely at n equal to n. Okay? You might ask what happens at m equal to n. So here is a plot of the smallest eigenvalue over the gram matrix, this gram matrix here. And then you can see that at that point, the smallest eigenvalue goes down to 0 very fast. So this is the one piece of experimental evidence, experimental result. The second piece of experimental result is that if you do this gradient descent algorithm and you stop at different times, say if you stop at 10,000, what is it? This is 10,000 steps. Then you get this curve, which is very far from this curve. But if you are really, really patient and you stop at 10 to the 12 time steps, then you got this curve. Then you get this curve, which looks very much like this curve. So this is so what happened here? Let's look at this in a little bit of detail. So what happens is that if you look at the different errors as a function of the number of steps, notice this is logarithmic. And these blue dots are the testing error. You'll see eventually the testing error becomes very large, But it started out here and decreases, and for a very long period of time, 4 decades, the test error is small, but eventually it becomes large. So if you're really, really patient and you stop here, yes, you get a very bad error. But if you're a practitioner, you didn't wait that long enough, you would stop here and you would get good error. You would get error. And the red line, you might wonder what the red line is. The red line is the norm of the solution. The norm of the solution stays bounded and then eventually increases. So why is this so? This can be analyzed in reasonable detail. But if I give you the simple explanation is that the eventual, the final result is the solution when this is equal to 0. This is an algebraic equation. So you would get, if you solve this algebraic equation, you would get things like 1 over lambda. If lambda is small, the error is large. But if you look at the dynamics, then you would have e to the minus lambda t. And if lambda is small, that e to the minus lambda t is very, very slow. So the occurrence of small eigenvalues makes your eventual error very large, but also slows down this deterioration a lot in a tremendous way. So here's the subtlety. On one hand, your optimal solution is really bad. On the other hand, this saves you. The dynamics actually saves you. This example is very special to this particular random feature model. But the phenomena, I would say, the phenomena that's illustrated here seem to be of much more general relevance. Okay, so this is the one sort of subtlety that I want to illustrate. On one hand, if there's eventual deterioration. On the other hand, this deterioration is very, very slow. And this resonance, I call this resonance. People call this double descent, but I call this resonance. This resonance is responsible. If you think about the wrong phenomena that I discussed earlier, so the classical wrong phenomena, the very same thing happens. It's due to resonance. The Gram matrix has small eigenvalues, and it's if you do a gradient descent to find the optimal solution, then you will see the same phenomena. Okay, so the third point: how do we present a well-posed? How do we look for well-posed formulation of machine learning? Well-posed meaning that things should not be so subtle. Okay, I'm not sure this subtlety can be removed, but can be avoided. But you know, in machine learning, there's a lot of subtleties. Can we produce models that are not so subtle? Models that are well-posed in some way. So I'm going to look into this. Here, just to present one viewpoint, namely continuous formulation of machine learning. So before I do that, let's look at an example. So this is the problem in image processing, say denoising. In the old days, you know, the way people do denoising would just be to apply some filters to the noisy image. So these filters can be, you know, Fourier, low pass filters, or different kinds of wavelet-based filters. So that's one way to look to perform denoising or to perform tasks in image processing. But there's another way. So this is sort of advocated by the mathematicians. So in this approach, we first write down a continuous formulation of our problem. So we're going to say that the denoised image is the solution of this variational problem, where F is a noisy image, U is the denoised image, and lambda is some constant. This is the total variation. So this is a regularized model. Now you might argue, well, whether this is really a good model. You might argue. Okay, but never mind whether this is a good model. My approach is just going to be, we're going to solve this model anyway. We're going to take this, discretize, and optimize. That's another way of looking at image processing. And it has produced a lot of very impressive results. So we're going to take exactly the same kind of approach. And we're going to look at first formulate machine learning in a continuous way, and then we discretize. So we're going to, we can discretize using different methods, algorithms. We're going to see that first of all, these conventional neural network models can be recovered this way. So this is very encouraging, that we're not losing anything. Secondly, if we do it this way, then we can sort of focus our attention on the continuous formulation of the problem to make sure that this continuous formulation is actually a good problem. It's not a bad problem to begin with. So then maybe whatever discretization would be robust. And continuous models are typically easier to analyze, as we all know. So let's look at how this works out. So to do this, we first have to think about how to represent our functions. So what do we mean by this? So a classical way of representing functions is through Fourier transform. So A will be the Fourier transform of F. So associated with this, we have the discrete Fourier transform. And this discrete Fourier transform suffers from curse of dimensionality because it's grid-based. There's a fixed grid. Now, the new idea, I put new in quotation marks, the new idea is to replace this representation, replace d omega here by a probability distribution pi d omega. Then to discretize this, we just have to Monte Carlo sample pi. And then according to what I would say earlier, we would have such an error rate where there's no curse of dimensionality. Okay, now why is this relevant? This is relevant because this expression here is nothing but a two-layer neural network with activation function given by e to the iz. So this is a two-layer neural network. And this slide here is essentially why two-layer neural network works from the viewpoint of approximation theory. There's another issue about the estimation error. But if you just think about approximation here, error, this is exactly what happens. Why that neural network, two-layer neural networks does not have curse of dimensionality. So this, we're going to represent functions this way, replacing E by general activation functions. So having this having this representation, then we can look at the population risk, which from the viewpoint of statistical physics is called the free energy. So we have a free energy defined by the population risk, and we want to minimize this free energy to find the optimal parameters. So this problem, has been dealt with, this kind of problem has been dealt with in statistical physics. In particular, there was a very well-known paper by Hopper and Homburg, two very distinguished physicists, in which they defined different kinds of gradient descent flows. For example, in here, we have both A and pi. These are our parameters. We want to optimize them. But A is a non-conservative parameter, order parameter in that context. Pi is conservative because pi is a probability distribution. The integral of pi is 1. So for non-conservative order parameter, we have the model A dynamics defined just this way. And this is where Alenkon equation comes from. For conserved order parameter, we define this kind of a dynamics. Namely, we first take the variational derivative. That's called chemical potential in physics. And then we define the velocity, then we define the current, and then we have the gradient flow defined by the continuity equation. This is how Hilliard equation came out. Okay, this gradient descent happened to be the gradient descent with respect to the Wasserstein metric. Okay, so these kinds of ideas were in physics. We just adapt them here. Now, to give an example, if we go back to the feature-based model, namely, we fix pi, we just look at A as being the variable we want to minimize, the parameter that we want to minimize. Then the Alenkon equation, the model A dynamics, looks like this. This is just for the coefficient, this is just a linear integral equation with the kernel K that defined earlier. And then for this kind of linear integral equations, kernel being positive definite, we have all kinds of nice estimates. Nothing goes wrong in the continuous setting, at least. Now, for the conservative case, for the conservative order parameter, here's another example. Then the gradient flow looks like this. Looks like this, PDE. It's not really PDE because D is non-local. D has this integral expression. And this differential integral equation is the same as the Minitutorial equations derived by 4 groups of people independently. Very nice work that gives rise to these equations. Okay. Now, next we discretize. Now, to discretize, we first discretize the population risk into the empirical risk using data. And then we discretize the gradient flow, either this equation or this equation. So how do we discretize that? Well, we can use spectral method. So this is a typical method. You can use finite difference, finite element, whatever. Ooh, time is run out. Okay, so I'll just go for a minute and then I'll stop. So we can use spectral method. And that works very well in low dimension. But we are in high dimensional context, we have to use the dynamic analog of Monte Carlo, which is the particle method. Also we can use smooth particle method. But anyway, if you use particle method to discretize these models, continuous models, you will recover exactly the gradient descent dynamics for the random feature model or for the two-layer neural network model. So this is what I was said here. Okay, the next section, as I suggested earlier, is the application of all these different viewpoints combined to look at deep neural network models. First is a remark that if you look at real, the standard deep neural network models, it's actually unstable. These standard fully connected deep neural network model is unstable when the number of layers grow large. So you have to think about ResNet, the residual network. And then for the residual network, we can apply all the things we studied earlier, and then we can, I'm going to skip all these. We have the gradient flow.
Weinan, I think we just had a reaction from the audience that they wouldn't mind if you take another 5 minutes or so.
Oh, okay. So then let's go back. Let's go back that in order to, so first how to look at this problem of residual networks from a continuous viewpoint. Remember, I advocated a continuous viewpoint. So so remember, for the continuous viewpoint, the first thing is to think about how do we represent functions. So I discussed this sort of generalized Fourier transform for which we replace d omega by pi d omega. So that's sort of a general integral representation of functions. To look at deep residual neural networks, we need to think about another kinds of representation, namely representing functions by flows, by solutions of dynamical systems. So here is an arbitrary set of ODEs where the right-hand side is some sort of arbitrary right-hand side. The flow map for this ODE is a nonlinear flow map. And by contracting that flow map with some scalar, with some vector, we'll get a function. So if you have lots of G's, you can produce lots of functions this way. Okay, but of course, what is the right G to choose? The answer is that the right of G to choose are these kind of guys. These are exactly the same as the integral representations I discussed earlier. So why do I claim that these are the right representation? There's a theorem later that shows that these are the right kinds of representations. But if we take that for granted at the moment, then we would have these kind of flows. So here the parameters are these coefficients A, and the probability distribution for the W at each time tau, solo time tau. So you solve this ODE to time tau equal to 1, and you apply a contraction. So this is a simple contraction that sums all the components. And then so this will be continuous representation. If you discretize, unsurprisingly, you recover the neural network, the residual neural network model. This is the typical ResNet. And we can do the same thing for flows. Flow meaning optimization. Remember that these guys are parameters we don't need to optimize in order to approximate a particular target function. So for that purpose, we need to look at gradient descent. So here, the gradient descent, we want to do gradient descent in order to produce these families of probability distributions. My sunroom is now getting hot. To produce this family. So the parameter here is this family of probability distributions rho. So in that space of one parameter family of probability distributions, we can define a generalized Wasserstein metric. And our gradient flow is just going to be the gradient flow with respect to that generalized Wasserstein metric. And it happened to be, it can be written in the following way. So if you know control theory, you recognize the connection here with this flow, which is the gradient flow with respect to this metric. You recognize this flow, the connection between this flow and the maximum principle in control theory. And as a matter of fact, you can see that there's a Hamiltonian here defined. So I can't go through the details because time is running out, but you can find details from the papers on my webpage. If you discretize this, you'll recover gradient descent algorithms for the ResNet, for the residual networks. And also, we have the approximation theory for the ResNet. And as a matter of fact, you start with some ResNet, and like thing. And these guys are I-dependent variables. You can show that continuum in the law of large numbers of these resonant-like thing corresponds to the kind of structures I showed earlier. So this is why, this is the answer to why I claim this, sorry, this is the correct choice of G. Okay, anyway, so we call this compositional law of large numbers. So this explains that you need to think about this. And then for these resonates, one can ask, what is the analog of barren space? What is the analog of reproducing Hilbert space? And that's defined here. Unfortunately, it's a little bit convoluted, so we call this compositional space and compositional norms. And then from these, you can show that there's direct and inverse approximation theorems. You can show if you regularize the model in the standard way, you'll get this 1 over m. Here is the L. L is the number of layers. L plays the role of m. And 1 over n kind of estimates that promised earlier. Okay, so summarize. I try to present a numerical analysis viewpoint of machine learning. And if you think about what is the core of numerical analysis? Well, it has two parts. First is to understand the physics. We'll take a conservation laws. You know, the thing I graduated when I was learning as a graduate student. Conservation laws for gas dynamics. We need to understand the physics. Physics associated with shocks. So here, there's no physics, but we have these phenomena. So, for example, the implicit regulation, the slow deterioration. This is only one phenomenon I explained in this talk. All the other phenomena I didn't explain very much. So we need to understand all these different phenomena. Secondly, we need to come up with a set of design principles. So here, the design principles that I advocated is continuous formulation, and then discretize. And we use Monte Carlo's benchmark. But from the viewpoint of analysis, the most important thing here is the new hierarchy of function spaces in high dimension. So reproducing Hilbert space, barren space, compositional function. These are the replacement of subloop spaces in high dimension. If you think about subloop space in high dimension, you cannot go very far because there's intrinsic curse of dimensionality. You have to think about these other guys in order to avoid curse of dimensionality. There are many open problems, but I just stop here. So thank you very much for your attention. I'm sorry I went over time.
No, thank you so much, Weinan. This was really an amazing, amazing presentation. Thank you so much.
Thank you.
Are you happy to take a few questions?
Sure.
Okay, so, and please, audience, post your questions into the chat if you have questions. So there is one quite specific question by Jia Hao Yao about your MC integrals. In the MC integrals, will the variance of G contain dimension factor or also be dimension free?
No,
I think that refers to the beginning of your talk. Yeah.
Right, that G depends on the function G. So if you have a G in D dimension, of course that's going to be, there's some dimensional dependence. The relevant question here to ask is that if you have a sequence of models, for example, in statistical mechanics, think about Heisenberg model in different dimensions and ask whether the variance would depend on dimension. The answer is yes. And it can be very large, exponentially large. This is certainly the case for spin glass models. So, but that's a different issue. So that's why we need to do dimension reduction. Variance reduction in order to do something simple. So the relevant question here is whether if you have a situation like that, these constants, the norms for say ResNet, whether these norms, how these norms depend on dimensionality. Well, we don't have general answers to that question, but for a few cases we've looked at, there is not necessarily bad dependence on dimensionality, but this is not conclusive at all, so I shouldn't say too much. But we do have run examples of sequence of problems in different dimensions, and we don't see tremendous dependence on dimensionality of these norms. But it's not.
I think, Weinan, there is a related question to this, which comes from Hai Liang Liu. And the question is, whatever representation is used, random feature seems crucial to be involved to overcome the curse of dimensionality, right?
I wouldn't say that. So random feature model happened to be a good starting point because it is a good starting point to think about two-layer neural networks. But if you think about ResNet, it has nothing to do with random feature model as far as I can tell. So I wouldn't say random feature model. No, it's a good model problem, but it's still linear. It's a good model problem. It's like when we learn conservation laws. You know, the linear advection equation is a good problem to start with, even though it's completely linear. So then the Burger's equation is like a two-layer neural network. The Euler equations of gas dynamics is like the ResNets. So if you want to make that analogy.
Yeah. Okay, so then there comes another more functional analysis question, Weinan, from Yuri Korolev about Barron spaces and composition norm spaces. And the question is, how large are they? What kind of functions live in them?
That's a very, very good question. So first, let me say the understanding of that is very primitive at this point. One can show that compositional function spaces are larger than Barron space. As a matter of fact, not just Barron space, all the cousins of Barron space are contained in compositional function space. The compositional functions is the largest at the moment, and the norm is the smallest. But if you want to ask precisely what kind of functions lies in those spaces, if you want to formulate this in conventional terms, like Fourier transform or derivatives, they're not this kind of categorization is not necessarily the best, because I think in high dimensions, think about derivatives is not a good way to look at functions. The better question to ask is, what about these solutions, high dimensional functions, say, for example, solutions of Bellman equations that arise from reinforcement learning, whether those functions lie in these spaces. So then this question is still open. And this, as a matter of fact, we're working on this right now.
Okay. We have one more question anonymously asked about reproducing kernel Hilbert spaces. So in RKHS theory, one must increase the smoothness of the feature map as dimension grows, such that the Sobolev embeddings still ensure continuity of functions. Do you have a similar property in your F2 spaces?
Well, we really don't care about the continuity of functions. Well, I guess we do, because we need to make sure that the function's values are defined. Yeah, my answer was wrong. I need to think about this. But
okay. Oh, fair enough.
Yeah, I need to think about this.
So, does anyone in the panel have a question? Because you can ask by unmuting yourself. Otherwise, I have a quite high level question just to round things off. So, Weinan, can you go in a bit more detail about what is it that you, what type of properties you want from the discretization of your continuum model to give a good neural network, to give something that has the properties that we want from predictors, from neural network predictors?
The most important property is the curse of dimensionality. You should not suffer from curse of dimensionality. So from this viewpoint, particle method is the top choice. And if you do particle method, you get neural network. Actually, from this viewpoint, you can see that neural networks are actually very natural, because they arise as the most natural discretization of these continuous problems. Other properties are stability in infinite time. So we're interested in the gradient flow at very long time. So you don't want some methods that sort of deteriorates as time goes on. So if there is a sort of another Lyapunov function, that would be best, because that ensures stability.
Super. Okay, thanks a lot. I think this partially also touches upon what will happen tomorrow in the session where Eldad Haber from UBC will give his talk about using ODE, PDE representations of neural networks.
Yeah.
Sorry, Weinan, did you want to say something
actually,
more?
One of the slides, his name is on one of the slides, but I didn't explain.
Yes, I've seen that actually, yes. Yes. And yeah, so this was really great. Thank you so much, Weinan, again, for this amazing talk. This was this was the first talk of 6 in our tutorial. So the second will happen tomorrow by Eldad. So please stay tuned and yeah, join again our virtual session tomorrow.
Thank you very much.
Thank you so much, everyone. Thank you, Weinan. Thank you.